Hello everyone. Today we're going to be learning about XOR and XNOR gates. So let's start with the XOR gate, short for exclusive OR. Let's say we have two inputs, X and Y, and one output Z. The exclusive OR gate is going to output a logic high or 1 for any set of inputs that have an odd number of 1s. So in our case with two inputs, 0, 1 has 1, 1, or an odd number of 1s, so that will output a 1 or a logic high. And 1, 0 also falls into this criteria. Whereas 0, 0 has 0 1s, which 0 is even, so that will output a 0. And 1, 1 has 2 1s, again even, so that will output another 0. Okay? Let's look at a CMOS example. So we got input X, Y, output Z. I'm going to go through all of the possible inputs and map the corresponding outputs. Okay, so for input 0, 0, you got 0 here, 0 there. This NMOS is off, no connection is made. This PMOS is on, however, this NMOS here is off, so no connection is made. However, if you look down here in the bottom right, these two PMOSs are both going to be on. So this ground gets connected to the two gates of these transistors here, which then turns this PMOS on and connects our output Z to ground, giving us an output of 0. Now, if we input 0, 1, this NMOS is off, this PMOS is off, this PMOS, is on, and this NMOS is also on. So VDD gets connected to the two gates of these transistors, which turns this NMOS on, connecting VDD to our output Z, giving us a 1 for our output. Now, on the flip side, if we input 1, 0, this NMOS is on, this PMOS is on. That connects VDD to the two gates of these transistors, turning this NMOS on, which connects VDD to our output Z, giving us an output of 1. And lastly, for input 1, 1, this NMOS is on, this PMOS is off. This PMOS is off, so VDD is not connected. However, these two NMOSs are both on, so ground is connected to the two gates of these transistors, which then turns this PMOS on and connects our output Z to ground, giving us an output of 0. So now let's look at an XNOR gate. Now an XNOR is just the inverse of an XOR. So if we have two inputs, X, Y, output Z, you can think of an XNOR like a XOR with an inverter on the output. So we know that an XOR outputs a 1 for an odd number of input 1s. So an XNOR outputs a 1 for an even number of input 1s. So for 1, 1, we have two input 1s, so we're going to output a 1. And for 0, 0, we have 0 input 1s, which is technically an even number of 1s, so we're going to output a 1. Now 0, 1 has an odd number of 1s, output a 0. 1, 0, again, has an odd number of 1s, output a 0. So this is the XNOR truth table. You notice this is the exact opposite of the XOR truth table. Let's look at a CMOS example. Again, inputs X, Y, output Z, 0, 0, 0, 1. Oops. 1, 0, and 1, 1. Okay, so let's start off with input 0, 0. We have input 0, 0. These two NMOSs are off. These two PMOSs here are on. That connects VDD to the two gates of these transistors, which turns this NMOS on, connecting our output Z to VDD, like so. Our output's 1. Now if we input 0, 1, this NMOS is off, no connection made there. This PMOS here is on, but this PMOS is off, no connection. 0, 1. This PMOS is on, this NMOS is on, so ground is connected to the two gates of these transistors, turning this PMOS on, which connects our output Z to ground, giving us an output of 0. Now on the flip side, if we input 1, 0, This NMOS is on, this NMOS is off, this PMOS is off, no connection made there. This PMOS is off, no connection. This NMOS is on, this PMOS is on. There's a connection from ground to the two gates of these transistors, which connects our output Z to ground, resulting in an output of 0. And lastly, for input 1, 1, we see these two NMOS transistors are on. VDD is connected to the two gates of these transistors, which turns this NMOS on, connecting VDD to our output Z, resulting in an output of 1.